So at the end of the last video, you saw that these two molecules require some doing to convert one to the other. And as such, we don't consider them to be conformers, we call them geometric isomers, or more specifically, cis-trans isomers. And that cis-trans thing refers to how we're going to differentiate them from each other, how we're going to explain to somebody that we mean to talk about that particular version of the molecule. Generally, calling something either cis or trans involves identifying whether the heavy, that is the non-hydrogen things in most cases, things are on the same side of the double bond or if they're opposite one another. And so the way your book will show you to do this is to think about a dotted line going through that double bond. And now what you're doing is you're asking yourself, what's the heavy thing on the left? What's the heavy thing on the right? And are they both pointing up? Or is one pointing up and one pointing down? Or are they both pointing down? If they're both pointing to the same side of the bond, we will call that a cis double bond. And so in this case here, which of the two would you say has the two heavy things, in this case the two CH3s, pointing the same direction? I hope what you decided was the one on the left, because here they're both pointing upward. Remember, this carbon, we can see a carbon attached to it via a single bond. We can see another carbon attached by a double bond. That means there must be a hydrogen over here and also a hydrogen over there. So notice how in this case, heavy things both pointing up, lighter things both pointing down. On the other hand, if they're pointing to opposite sides of the bond, we call that a trans double bond. And so the opposite sides, in this case, heavy thing pointing up, light thing pointing down on the left, heavy thing pointing down, light thing pointing up on the right. So this would be trans 2-butene. And notice that the cis or trans designation, which you'll be asked to put on a few molecules during your homework, goes at the very, very beginning of the compound's name. Now, bear in mind, this will only apply when neither of the alkene carbons has two identical things attached to it. A very simple situation would be one where two hydrogens are attached on one side. So for example, this molecule, 1-butene, would have two hydrogens attached to the left side carbon. So there's no heavy thing for me to compare to what's going on the right side, so there's no cis-trans isomers. Thought of another way, if I were to swap the positions of the two hydrogens on the left, you'd never know. Whereas if I swap the CH3 with the H on this one, I turn this into that. Now before we do a little bit of practice, it's worth noting there is one other kind of molecule that can have cis-trans isomerism besides an alkene, and that's a cycloalkane. Because if you look at the way this thing is built, because these carbons are all attached to each other, the things on the top of the structure and the things on the bottom of the structure can't easily swap places without either breaking the ring or breaking their own bonds to the ring. Keep that in mind as we start the next little exercise. What I'd like you to do for each of these four molecules is give the structure a good look, particularly focus on the ring or on the double bond, and ask yourself, could you draw cis and trans isomers of this particular molecule? Pause the video, give it a try, and when you come back, we'll evaluate them ourselves. All right, what I hope you've come up with after giving this a good think is that this one and this one, sorry about banging the camera there, would be able to have cis-trans isomerism, whereas this and this aren't going to be able to. Now, this one I think is kind of a prototypical version of an alkene that doesn't have isomerism because this has two hydrogens on that side. So this is very similar to 1-butene. In fact, this would be 1-hexene, and it would have the two H's on the far right side. Switching their positions doesn't change what the molecule is, and so we don't have any cis-trans isomerism there. We just have a single molecule called 1-hexene. Similarly, if I look at this one, the chlorine could be pointing towards me or away from me. It could be pointing up from the ring or down from the ring. But much as is the case here with the hunk of carbon that's attached on the left side of this double bond, there's nothing for me to compare that chlorine to. There's nothing else bound anywhere on this ring that I would say is on the same side or on the opposite side of that chlorine. So again, this isn't going to have a whole lot going on. We would just simply call this chlorocyclohexane. But not much else to it. No cis, no trans. On the other hand, These are both great examples of something that could have two different isomers. This double bond on one side has an H and then CH2CH3. On this side, an H and then CH2CH2CH3. Those could be arranged in either situation, either orientation to each other. So I could have a version where they both point up. So I know I've got 2 carbons on the left, 1, 2, and then 3 carbons on the right, 1, 2, 3. And this would be cis 1, 2, 3 heptene, because I've got 7 total carbons in here, and the double bond is in that spot, and I've drawn the cis version. The trans version I find easiest to draw by just simply doing a standard zigzaggy serpent, because that's going to give me the right orientation. And I did octane again. What is wrong with me today? There we go. There are our 7 carbons. 1, 2, 3. I'll put the double bond right there. That would be trans 3 heptene. Now, as for the cycloalkane, here's where the models can help out an awful lot. If I look at this model that I've made of that particular molecule, so here you go. There's the 5-carbon ring, CH3 on this side, OH on that side. When I originally made it, I happened to put them both pointing up from the plane of the ring. Now, since you're looking at it this way, that means they're both coming at you. So remember what we did on the molecular models lab. If we wanted to show a bond coming out of the page, we used a wedge. And if we wanted to show it going back into the page, we would show a set of dashes. So if I want to draw a version where they're pointing in the same direction, I want to make sure whether I choose wedge or dash that they're both going the same way. If I want trans, then I'm going to have 1 wedge, 1 dash. So I see that one's coming at me out of the page and one's going away from me into the page. So here's how those would look. I start with my 5-carbon ring, and we go wedge, wedge, CH3, OH. This would be the cis version of this. If you're interested, it would be 3-methyl cyclopentanol. Notice the OL is indicating I've got an alcohol in this thing. You are not responsible for being able to do that, but it's kind of neat to see. On the other hand, if I want to draw the trans version of all that, then I just simply need to pick one of these and keep it as a wedge and put the other one back into the board. And that would be the trans version of 3-methyl cyclopentanol. Now, you would be forgiven at this point in the class for thinking to yourself, oh dear heavens, that is so nitpicky, who cares? Well, I'm going to show you why you care. You remember back when we started studying radiation, and I mentioned how visible light is only visible because we happen to have evolved cells and molecules that can absorb that particular kind of light. Any guesses what the molecule does when it absorbs that light? How it is that it changes? Let's have a peek. So what you're looking at here is retinal, which is a derivative of vitamin A, otherwise known as retinol. And a couple things that are worth noticing here. This is retinal because it has this functional group right here on the right side. This is a carbonyl that has an H attached to it. You might remember that's called an aldehyde. So it's retinal for that reason. You might guess that when it was retinol, it used to have an OH in that position, not a C with an O and an H, and was an alcohol. Now, the other thing worth noticing about this is that it's trans retinal, and admittedly, most of the bonds you can see here appear to be in the trans configuration, but this is referring specifically to that one. Because what happens when a photon of visible light is absorbed by your eye and in the retina is that the difference in energy between this state and the cis version of retinal, where all of this junk here flips downward, the difference in energy between those states is roughly the same as the energy of that light. And as a result, when it flips like this, you've turned it into a high energy version of itself, it's not stable, and sooner or later, it's going to flip back. And when it goes back to trans, that energy is used to start a cascade of chemical reactions that eventually end at the brain with the perception of sight. Pretty wild, huh? All starts with a cis-trans isomerization.